In this video, I will be going over problem number 9 from the textbook, page 138. And you're given the graph of velocity, and they ask you a series of questions, A, B, C, and D, and they all have to do with the graph of velocity. And part A is asking, when does the particle move forward, move backward, speed up, slow down? So the nice thing about this graph is that it is the graph of velocity, so it's straight input, output. So if we're above the horizontal axis, that's where velocity is positive. So velocity is greater than 0. And if the graph is below the horizontal axis, that's where velocity is negative, or velocity is less than 0. And a particle moves forward when velocity is positive, so it'll be moving forward in the intervals from 0 to 1 and 5 to 7. And a particle moves backwards when the velocity is less than 0 or negative, so that'll be in the interval from 1 to 5. So the particle moves forward when the velocity is positive, which is on the interval from 0 to 1 and 5 to 7. The particle moves backward when the velocity is negative, which is on the interval from 1 to 5. Now, I still need to talk about speed. When does the particle speed up and slow down? But before I can explain that, I need to bring up some points. So I'm going to give you some notes to jot down. When velocity is positive and acceleration is positive, the particle is speeding up. If velocity is negative and acceleration is also negative, then the particle is also speeding up. So these are two cases where the particle is speeding up. Now, the signs have to be the same for velocity and acceleration for the particle to be speeding up. If the signs are different, so if velocity is positive and acceleration is negative, or if velocity is negative and acceleration is positive, this is where the particle is slowing down. Slow down. Now, I know I haven't talked much about acceleration, only velocity. And I mentioned that if you're given the position function s equals f of t, then velocity is the derivative of the position function s with respect to time, or f prime of t. So the velocity is the derivative of the position function. Acceleration is going to be the derivative of velocity. And if you think about it, if acceleration is the derivative of velocity and velocity is the derivative of the position function, then acceleration is the second derivative of f, or f double prime of t in this case. So this is something that we'll be making use of later, but not really for this problem. Right now, I want to make a point that acceleration is the derivative of velocity. So if I look back at my graph for velocity, I can easily get acceleration. Now that I know that acceleration is the derivative of velocity, I can easily get information for acceleration by looking at the slope of this graph. So the graph has a negative slope there, and there. So this is where acceleration is less than 0. This graph of velocity has a slope that's positive here. So this is where acceleration is greater than 0. So if you remember from earlier in the video, I said that from 0 to 1, velocity is positive, and from 1 to 2, velocity is negative because it's below the horizontal axis. So from 1 to 2, velocity is negative and acceleration is negative. So my particle is speeding up in the interval from 1 to 2. Now, if we look at the interval from 3 to 5, I have acceleration as positive, but velocity is negative because it's still below the horizontal axis. But from 5 to 6, it jumps up to the positive, velocity is positive, and acceleration is also positive from 5 to 6. And that's where the particle is also speeding up. So from 5 to 6, the particle is also speeding up. It's starting to get messy, so let me go ahead and erase some of the stuff. Right now what I'm trying to look at, or what I'm trying to help you understand, is where the particle speeds up. So right now I've highlighted where the particle speeds up, and that is on the interval from 1 to 2 and 5 to 6. Now let's look at where the particle slows down. So acceleration and velocity need to have different signs for the particle to be slowing down. And if you look at the first part, from 0 to 1, the first interval, from 0 to 1, my velocity is positive, yet the slope of velocity is negative, so acceleration is negative. So we know that the particle is slowing down in the interval from 0 to 1. Let me erase the other stuff. Okay, we already said that it's speeding up in the interval from 1 to 2. But if we look at the interval from 3 to 5, my velocity is negative, yet velocity is the graph of velocity has a positive slope there, so acceleration is positive. So the particle slows down on the interval from 3 to 5. Then its velocity is positive and acceleration is positive. We already talked about that for speeding up. But 6 to 7, velocity is positive, yet acceleration is negative, so it slows down. So we have 3 intervals where the particle seems to be slowing down. So here are your 4 answers to part A. And don't forget to highlight your answers. Okay, part B seems to be kind of redundant because we already talked about acceleration, and acceleration being the derivative of velocity. So we're going to have to be looking at the slope here. So we have a negative slope, therefore therefore acceleration is negative. Then we hit a slope of 0, so acceleration is 0. After that comes a slope that's positive, so acceleration is positive, then a negative slope, and finally another slope that's 0. So then we have acceleration is positive in the interval from 3 to 6. Acceleration is negative in the interval from 0 to 2 and the interval from 6 to 7. And then acceleration is 0 in the interval from 2 to 3 and the interval from 7 to 9. Okay, so part C wants to know when the particle is moving at its greatest speed. So to answer part C, I'm going to bring up the fact that speed is the absolute value of velocity. So if we have the graph of velocity, what would the graph of the absolute value of velocity look like? Think about that. What would the graph of the absolute value of velocity look like? And I try to highlight in red what the graph of the absolute value of velocity would look like. Pretty much whatever's positive stays positive, and the negative becomes positive. So it's a reflection of this negative portion. So this is not part of the absolute value of velocity. It's a reflection across the horizontal axis because everything that's negative becomes positive. And then after t equals 5, what's positive stays positive, it's positive, so it stays positive, and 0 is fine. So from t to 9, from the interval from t to 9, it's 0. It stays 0. So this is the graph of the absolute value of velocity, which is speed. And notice that it reaches its greatest speed, its highest points, it's going to be at t equals 0 and the interval from 2 to 3. So that'll be your answer for part C. T equals 0 and 2 to 3. Alright, now part D. When does the particle stand still for more than an instant? So if it's standing still, velocity is 0, but you can't necessarily look at just the zeros, because at t equals 1, velocity is 0, but it changed direction, so it was positive. It was moving in the positive direction, and then it changed direction really quick, and then it started to move in the negative direction. Okay? So it's not, at t equals 1, the particle did not stand still for more than an instant. It actually just stood still for an instant. Same thing happened at t equals 5. It quickly went from negative, 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 so it's moving in the negative direction. This particle is moving in the negative direction. Then it's quickly 0, but then it changes to a positive direction. So the particle was not still for more than an instant. It was a quick instant that it was 0 at t equals 5. And then at t equals 7 all the way to t equals 9, in the interval from 7 to 9, the particle was stood still. The velocity was 0, so it's in this interval that the particle stood still for more than an instant. And that's the answer, the interval from 7 to 9. And that wraps up problem number 9. That's how you would do problem number 9.